All right. So B3. So in this case right here, right, the question is asking for us to give the name, the possible magnetic quantum numbers, and the number of orbitals for each sublevel with the given quantum numbers. So if we look at A, right, what we're given is two quantum numbers. We're given n equals 3 and L equals 2, right? So n equals 3 is going to be the principal quantum number. L equals 2 is going to be the magnetic angular quantum number, right? So the first thing, jumped ahead for some reason. Right, so what we can see right there, first things first, right, in terms of the name of that orbital, right, we know it's going to be a 3 orbital, right, 3 at the beginning because n is equal to 3, and then for L is equal to 2, right, when L is equal to 2, that's going to give us a d orbital, right, so we're looking at 3 d orbitals in this case right here. And so now in terms of the remaining quantum numbers that are still left, right, there's still m sub L that hasn't been defined yet, right, and so that can be, anything that goes from plus 2 to 0 to minus 2 in that case, right? Because it goes from L to 0 to negative L in those cases. So you have, 5 different ones that are possible in those scenarios. And then there's also, right, the m sub s, right, the spin quantum number in these cases, right? But we're not necessarily worried about that specifically, right? Because we're really trying to just look at the orbital. And you only need those 3 quantum numbers to look at the orbital, right? So we have the 3D, and so there's 5 different possibilities that you can have for a 3D orbital in this case. Next one, right, we have n equals 2 and L is equal to 0. So now, again, right, because n is equal to 2, right, we know that that's the principal quantum number. That's going to give us the name 2, the name for the orbital. In this case right here, right, L is equal to 0, and so when L is equal to 0, that's going to be your s orbital. So the orbital's name is going to be 2s. And then again now, right, the remaining quantum number is going to be m sub L, and so that in this case right here is going to go from L to 0 to negative L, but because L is equal to 0, right, it's going to go from 0 to 0 to 0, which is all the same and everything, right? So there's only going to be m sub L is equal to 0, and there's only one orbital that matches the given quantum numbers of n is equal to 2 and L is equal to 0. In a scenario, right, where you have n is equal to 5 and L is equal to 1, again, right, the principal quantum number is going to be the first part of the name, right, so that's going to be 5. When L is equal to 1, right, this means that we're looking at a p orbital now in this case, and so we have the 5 p orbitals that we're looking at. And then the remainder, right, is you have your m sub L, and so again, it goes from positive L to 0 to negative L, so it's going to go from plus 1 to 0 to negative 1, right? Those are all of the different possible quantum numbers that you can have in those cases for that, and that means then that we have 3 orbitals that can have those quantum numbers. For D, right, we have n is equal to 4, L is equal to 3. So now, right, n is equal to 4. So that means that it's going to be, a 4 quantum number. When L is equal to 3, right, that means that we're looking at the f orbitals in that case, right? So we have that right there. And so now for m sub L, right, what we have is that it goes from then positive 3 to 0 to negative 3. And so that means that we end up with 7 orbitals in that case.